Good afternoon, and welcome to today's webinar, Chiplet Interconnect Testing Using JTAG Boundary Scan. My name is Heidi Richards, and I'm the Director of Compliance and Continuous Improvement at Asset Interconnect. Asset is the leading provider of ScanWorks platform for hardware validation and test, and the SourcePoint platform for software debug and trace. Before we get started, I'd like to go over a few housekeeping items so you know how to participate in today's event. First and foremost, today's webinar should run approximately 40 minutes. During that time, you will have the opportunity to submit text questions to today's presenter by typing your questions into the question pane of the control panel. You may send in your questions at any time during the presentation. We will collect these and address them during the Q&A session at the end of today's presentation. You will also have the ability to participate in poll questions, so be prepared to participate. On that note, please be sure to download a copy of today's presentation, which can be found as a handout in the control panel of your screen. Now, without further ado, we will turn the time over to our presenter, Michael Johnson. Michael serves as Project Manager for ScanWorks Boundary Scan for Asset Interconnect. He also serves as Manager of Asset's Application Engineering Organization. As Project Manager, Michael is responsible for providing strategic direction to Asset's Boundary Scan product line while coordinating with Asset's cross-functional team to bring the company's goals to fruition. Over to you, Michael.
Thank you, Heidi, for that kind introduction. Hello all, and thank you for attending this webinar where I will delve into the topic of chiplet interconnect testing using JTAG Boundary Scan. This topic is relevant due to the number of advanced packaging methodologies that have emerged within the semiconductor industry. The topic of chiplet interconnect testing using JTAG Boundary Scan is quite expansive, and our time today is limited. However, I hope you'll find this webinar informative. I'll leave some time for a Q&A at the end of the presentation. I'll also make my contact information available for questions or discussions outside of this webinar. The presentation will follow the agenda displayed. First, I'll provide an overview of the emergence of chiplet-based multi-die package devices. From there, I'll discuss the drive toward chiplet-based multi-die devices and how this advanced packaging methodology has extended Moore's Law. Next, I'll discuss the interconnect structures between chiplets. Once we discuss the interconnect structures, we'll discuss digital test patterns used to uncover interconnect structural faults. From there, I'll present an overview of the standard test interface language, also known and pronounced as STIL. Then I'll present a brief overview of Asset's ScanWorks Boundary Scan test tool for generating STIL. And lastly, I'll provide summary statements. The semiconductor industry is facing a new era in which device scaling and cost reduction will no longer continue on the path followed for the past few decades. Packing more transistors onto a monolithic chip has become more difficult and expensive. Semiconductor companies are looking for technology solutions to bridge the gap and to improve cost and performance, while at the same time adding more functionality to their chips. This search has led to the packaging innovation known as heterogeneous integration. Heterogeneous integration uses advanced packaging methodologies to integrate devices which can be separately designed and manufactured by the most suitable process technology and in the most optimized way. The drive toward chiplet-based multi-die devices began in the 1970s with a packaging innovation approach consisting of placing multiple interconnected chips on a package scale substrate. These devices became known as multi-chip modules, as pictured on the timeline. Over time, advanced packaging innovations continue to evolve, with innovations such as system in a package, system on integrated chip, 2.5D IC and 3D IC designs, up to the disaggregated system on chip packages, also pictured on the timeline. A chiplet is an integrated circuit block that has been specifically designed to work with other chiplets to form larger and more complex chips. So heterogeneous integration combines diverse chiplets into a functional system. Chiplets within multi-die devices can be selected, arranged, and assembled based on the desired chip functionality. Monolithic designs are difficult to scale past a certain size, and manufacturing large chips that contain more functions is more expensive. Taking these facts into account, the semiconductor industry needed a way to scale products to increase performance, deliver high silicon yields, while lowering prices. As an example of the progression of advanced packaging, AMD's first generation EPYC processor migrated from a monolithic design to an MCM, utilizing 4 interconnected 8-core processors. Moving forward, AMD designed chiplets to handle specific processor tasks. AMD's second generation EPYC and third generation Ryzen processors offered increased scaling and allowed each piece of silicon to be optimized to deliver the best latency and power characteristics using small 7 nanometer and 14 nanometer chiplets. Advanced packaging innovations has produced smaller packaging due to the small chiplets and 3D die stacking, lower power devices. Each chiplet can be optimized for the best power characteristics, greater chip configurability. Chiplets can be switched in and out of packages based on the function needed. Faster chip time to market. Individual chiplets can be drawn from a library of known good die, and reduced overall manufacturing costs. Chiplet production is more cost efficient. And now I'll pause for Heidi to ask a poll question.
Thank you, Michael. Our first poll question is, are you working on a chiplet-based design now? Please select the appropriate answer. Looks like a number of you have responded. Those of you who have not responded, go ahead and submit your response now, and we will close the poll in a few moments. We are now closing the poll, and I will share with you the results. It looks like the majority of folks picked yes. Now, back to you, Michael.
The push within the semiconductor industry has been to produce smaller, faster, and less expensive chips. This is an ideal that dates back to 1965, when Gordon Moore of Intel theorized that by shrinking transistors, it will be possible to double the number of transistors that fit onto an IC every 2 years. This became known as Moore's Law. Moore's prediction has held true, for the most part, for more than 50 years. But now Moore's Law is slowing. The cost of yielding large die continues to increase. As illustrated in the charts created by ARM and AMD, the physical gate length of a transistor has decreased, or at least plateaued, over time, while the cost to produce usable die has increased. The cost per die yielded has doubled from producing 14 to 16 nanometer die to 7 nanometer die. Gordon Moore went on to state, it may prove to be more economical to build large systems out of smaller functions, which are separately packaged and interconnected. So, one solution to easing the economics of manufacturing chips with a large amount of transistors is to break down a single chip into multiple smaller chiplets. Gordon Moore foresaw that heterogeneous integration would move the semiconductor industry forward. The implementation of multi-die devices will improve chip performance, allow for greater chip functionality, and chip configurability. One of the challenges associated with heterogeneous integrated designs is accommodating the large amount of data moving between each chiplet when in operational mode. While enormous strides have been made in advanced packaging solutions, choosing an interconnect technology that will accommodate large amounts of data and is compatible with the packaging solution is important. The ideal multi-die interconnect technology is scalable, has low power, it's area efficient, and buildable in a low-cost silicon and packaging technology. These are 3 classes of die-to-die interconnect technologies used in multi-die devices: multi-reach and long-reach serializer, deserializer, also known as SerDes, short-reach and ultra-short-reach SerDes, These die-to-die interconnects accommodate high-speed data transfer while minimizing noise and minimizing the number of interconnects, the die-to-die interconnects. And parallel interfaces are also used. Technologies such as high bandwidth memory, advanced interface bus, or bunches of wires are simple to implement and have a high bandwidth, but they do require a lot of wires to completely implement these solutions. And now, Heidi, I'll pause for you to ask another poll question.
Thank you, Michael. Our second poll question is, I test my die-to-die interconnects with boundary scan, functional test, or not tested. Please select the appropriate response and click Submit. Looks like a number of you have responded, so those of you who have not had a chance to respond, go ahead and submit your responses now, and we will close the poll in a few moments. We are now closing the poll, but I will be sharing the data with you. It looks like 71% of you chose boundary scan. Now back to you, Michael.
The MCM pictured is an Ethernet chip and has 8 surrounding chiplets that provide 6.4 terabytes of data to the switch core when in operational mode. To accommodate this high-speed transfer while minimizing noise, SerDes is used for the chiplet die-to-die interconnects. In terms of signaling schemes, the technology options for die-to-die interconnects are a parallel interface, non-return to zero, or known as NRZ, and pulse amplitude modulation 4, or PAM4. Parallel interfaces are used when lower bandwidths are required. The NRZ and PAM4 signaling schemes are utilized when a SerDes methodology is selected, which requires higher bandwidths. The optimal D2D connections within a multi-die device lie in the desire to optimize 6 often competing but interrelated factors. Those factors are cost, and that's the cost of the implementation, the die area available on the chip, power consumption to make sure it's within the design limits, scalability, and complexity. Now, there are requirements for testing multi-die devices. First, there must be access to the die-to-die interconnects, and the multi-die device must support several IEEE test standards. In particular, IEEE 1149.1, which is the standard for test access port and boundary scan architecture, IEEE 1149.6, boundary scan standard for advanced digital networks, and IEEE 1838, standard for test access architecture for three-dimensional stacked integrated circuits. Boundary scan test patterns can be used to determine opens, shorts, stuck-ats, and bridging faults. Undetected defects can result in chip performance degradation or chip failure. Since multi-die devices and die-to-die interconnects are reminiscent of interconnects between chips on a printed circuit board, test methodologies that apply to printed circuit boards can apply to testing multi-die device D2D interconnects. IEEE 1149.1 and 1149.6 patterns are suited for structural testing of die-to-die interconnects comprising the multi-die device, whether it's in a 2.5D chip or vertically stacked 3D chip designed by the IEEE 1838 standard. When testing die-to-die interconnects, possible shorts, opens, stuck-ats, and bridging faults must be considered. Since the boundary scan path in each multi-die device provides direct access to these nets, test patterns can be generated which provide coverage for these faults. There are several preferable patterns which detect possible faults. A walking once test tests interconnects between chiplets of the multi-die device. The walking one pattern involves transmitting a single one on the first net during the first vector step, while the other n-1 nets are set to 0. At the second vector step, the 1 is applied to the second net, while the other n-1 nets are set to 0. In this way, the 1 is applied and walks across all n nets in as many steps. The graphic to the right demonstrates this concept of walking ones on a group of nets applied by the transmit boundary scan cells on the left and the value captured by the receiving boundary scan cells on the right. The values in red indicate bit miscompares due to faults. Although walking one will uncover structural defects, the number of test steps grows linearly with the number of nets tested. Thereby, a large number of vectors are generated. So this might not be the most efficient algorithm to test our nets. A walking zero test can be used to test interconnects between chiplets of a multi-die device. The walking zero pattern involves transmitting a single zero on the first net during the first vector step, while the other n-1 nets are set to 1. At the second vector step, the 0 is applied to the second net, while the other n-1 nets are set to 1. In this way, the 0 applied walks across all n nets in as many steps. The graphic to the right demonstrates the concept of walking zeros patterns on a group of nets applied by transmit boundary scan cells on the left and the value captured by the receiving boundary scan cells on the right. The values in red indicate bit miscompares due to faults. As with the walking ones test, the walking zero test will uncover structural faults, but the number of test steps grows linearly with the number of nets tested. Thereby, a large number of vectors will be generated. So again, the walking zero test will uncover faults, but it may not be the most efficient algorithm used to detect faults. And now I'll pause again for Heidi to ask another poll question.
Thank you, Michael. Our third and final poll question is, interconnect structural defects and boundary scan cell design defects are the options: a big concern, not that important, not sure. Go ahead and submit your responses now, and we will close the poll in a few moments. It looks like a majority of you have responded. Those of you who have not yet responded, go ahead and submit your responses now, and we will close the poll. We are now closing the poll, but I will be sharing the results with you. Looks like the majority of you identified a big concern. Thank you, Michael. Back to you.
Another type of pattern used to detect shorts, opens, stuck at, and bridging fault conditions on die-to-die interconnects of multi-die devices are Wagner patterns. Wagner patterns are extended binary count patterns, and the Wagner algorithm provides 100% fault coverage for shorts, opens, stuck at, and bridging faults between die-to-die interconnects. The number of test steps grows logarithmically, not linearly, with the number of nets tested. So Wagner patterns minimize the number of vectors while providing maximum fault coverage. Also, Wagner patterns do not require pairing with other patterns, such as pairing with the walking ones test or the walking zeros test to increase their fault coverage. The graphic to the right demonstrates the concept of Wagner patterns on a group of nets applied by transmit boundary scan cells on the left and the value captured by the receiving boundary scan cells on the right. The values in red indicate bit miscompares due to fault. Again, Wagner patterns are the most efficient patterns for optimizing test coverage and diagnostics. IEEE 1450, the standard test interface language, also known as STIL, provides a means of describing digital test patterns and waveforms as a common test language. The EDA to test flow is filled with many different formats for test information. Different formats exist not only for the interface between EDA tools and IC vendors, but also for the interface between IC vendors and automatic test equipment or ATE vendors. Because of these differences, a standard language was needed. STIL, which was standardized back in 1999 by the Tools and Test Consortium and consisted of corporate leaders in both the IC and ATE industries. STIL test patterns and waveforms can be generated by electronic automated design or EDA tools. STIL was created in response to specifically address growing concerns in creating large volumes of test data by EDA tools and their ability to transfer this digital test data between various platforms. There was no direct interface between the EDA tools and the IC vendors, nor was there a direct interface between IC vendors and AT equipment. Therefore, STIL is beneficial to the EDA vendors who create the test data, the IC vendors who manipulate the test data, and the AT vendors who accept the test data. STIL can be ported to chip automated test equipment, ATE, for application to D2D interconnects. Once ported, STIL patterns are applied to the D2D interconnects via the boundary scan cells. STIL consists of 7 blocks. We have a header block, there's a signals block, signals group block, a timing block, a pattern burst block, a pattern exec block, and a pattern block. The example on the right is STIL that has been produced by ScanWorks and consists of 3 sections: the signals block, the signal groups block, and timing block. The signals block describes each signal of the die and its function. The signal groups block is used to create named references to the signals group. The timing block defines the placement of timing edges and the format of the cyclized waveforms that is referenced by applying waveform characteristics to signals in the vector statements. The waveform table within the timing block table contains the information that produces the digital patterns applied to the die-to-die interconnects by forcing boundary scan drivers either high, low, or off, and sets boundary scan receivers on the die to receive the scans for comparisons. ScanWorks now includes an option to post-process die-to-die test pattern data to STIL for application to multi-die, die-to-die interconnects on chip ATE. Since its inception, as its ScanWorks for Boundary Scan tool, the test platform has provided board-level shorts, opens, stuck-at, and bridging fault testing for interconnects between boundary scan devices through the use of its automatic test pattern generator feature. With recent enhancements, ScanWorks now generates patterns based on STIL that can be applied by chip ATE to test for shorts, opens, stuck-at, and bridging faults on die-to-die interconnects between chiplets. ScanWorks ATPG feature produces test patterns based on the chiplets BSDLs and the package netlists describing how the chiplets are interconnected. Using the ScanWorks STIL option has several key value features for chip manufacturers and board designers. Multi-die device suppliers can provide the ScanWorks project used to generate the STIL patterns to downstream board designers and contract manufacturers. Board designers can apply die-to-die interconnect tests to the board and to the multi-die device to confirm its quality. Problems found with the multi-die device can be tracked and traced back to the package supplier who has the same test on their ATE to help debug whether it's a board or multi-die package issue. So, in summary, advanced packaging innovations are being adopted by the semiconductor industry to achieve the economic advantages that were previously met with silicon scaling. Multi-die devices are an important innovation approach towards diverting from monolithic die designs over to more manageable and less expensive chiplet-based designs. While it is technologically possible to continue scaling monolithic designs, the economics do not favor this approach. Multi-die device die-to-die interconnect testing is important for validating the chip. The use of chiplets will become a game changer for the semiconductor companies that can master this design and this new approach. Die-to-die interconnect testing can be accomplished through boundary scan on chip-ATE using STIL. Static testing for structural faults using the various digital test patterns can be converted to STIL, and these tests run in just a matter of seconds. And lastly, ScanWorks provides an automated and scalable die-to-die interconnect test authoring solution that is deployable through the entire life cycle of a multi-die device. So I'd like to thank you all for your time and attention this afternoon. Heidi, are there any questions from our audience?
Thank you, Michael. There are some questions. As a reminder, you can still submit your questions through the question pane in your attendee control panel. Michael, our first question is, how do I get started with ScanWorks to produce a STIL to test my multi-die device?
Okay, thank you, Heidi, for that question. If you're just starting, you'll first need to create a ScanWorks project and a design, as you normally would. We've got our ScanWorks user on the line. You know how to create a project and a design. So you would start out there as normal. Then you would import the chiplet BSDLs and the netlists. Again, the same steps that you would take in your normal ScanWorks project development flow. So within the ScanWorks 4.8 installation, and I will mention that this STIL option feature was implemented with our ScanWorks 4.8 release. So within the ScanWorks 4.8 installation, in the documents folder, there's a document named STIL option usage instructions. This is a step-by-step document that will instruct you on how to get started using the STIL feature within ScanWorks.
Okay, thank you, Michael. Our next question is, you mentioned that Moore's law is slowing down. Can you explain?
Sure, thank you for the question. So in a nutshell, we're not seeing the same trends that we were seeing just a short number of years ago, where we were able to pack more transistors onto chips, like the doubling of transistors every 2 years, and also seeing that cost go down. So this led to the advanced packaging innovation that I've discussed in this presentation. With multi-die devices, it just makes sense to shrink die from the 14 nanometer substrate down to 12, and now even down to 7, and build chips from those individual chiplets to perform individual functions. That's the starting point for this chiplet approach. It's just become more complicated and expensive to build complete monolithic chips at smaller die sizes.
Okay, thank you, Michael. I do have another question here. The question is, how do you handle the multiple BSDL files for the various dies in the chiplet?
Okay, good question. So within ScanWorks, there's an import feature where you would import your BSDLs. And upon the first importing of those files, you would do what's called a build, or perform what's called a build. And that translates the BSDLs from just the text format into a binary format that can be used by the tool, by ScanWorks. So that's the first step. The second step after you import the BSDLs and perform the build is you would arrange those BSDLs or those chiplets in the order from TDI to TDO that is described by the chiplet. So you will need a little internal information from the device manufacturer on the order of the particular chips. one chip would need to go. The first chiplet closer to TDI would need to be inserted first into the scan path, and then the second BSDL or the second chip, and so on and so forth. So you have to know the proper ordering of the chiplets in the package from TDI to TDO. But it's a very simple procedure, and ScanWorks pretty much handles that for you as long as you know the order of the chiplets within the particular package.
Okay, thank you, Michael. Another question is the style option part of the standard ScanWorks license, or is it an additional license?
The style option, it is not part of the standard test development or manufacturing license. It is an additional option that you would add on. So you would speak with your salesman about adding that option on, but it is not part of, again, the standard test development license or the manufacturing license. It is one of our additional add-on license features.
Okay, thank you, Michael. And another question is, are Wagner patterns considered more stressful than walking ones or walking zeros?
I would say yes, they are. They are considered more stressful because a walking one pattern, as I mentioned in the presentation, may need to be complemented or paired with the walking zeros pattern just to make sure that you're getting complete coverage for opens, shorts, stuckats, and bridging faults. The Wagner patterns use a binary count pattern that it is extended. And it has minimum vectors as well. So it is a more stressful pattern to apply to your die-to-die interconnects to make sure that you're capturing any defects more so than just a walking ones test, a walking zeros test, or even the combination of the two, running a walking one test and a walking zeros test. So yes, it is more stressful and will uncover more defects, potential defects than the walking one or walking zero pattern.
Thank you, Michael. It looks like we're running out of time for answering questions. Michael, is there anything else you want to cover before we do a wrap up?
Well, I'd just like to say, I want to thank everyone for joining today and taking time out of your busy schedule to attend this webinar. I invite each of you to contact me should you need any additional information on ScanWorks and the style option. And I'll also like to invite each one of you to visit our website to learn more about Asset's additional test and debug product offerings. So thank you and good afternoon.
Thank you, Michael. And thank you everyone for attending today's webinar, Chiplet Interconnect Testing using JTAG Boundary Scan. If you have any other questions, please be sure to make a note of Michael's contact information listed on the last slide of the presentation. As you exit today's webinar, we'd appreciate it if you'd complete a survey on the presentation and provide your feedback. You will also receive a follow-up email within 24 to 48 hours